Hello, AP Chemistry students. This is now section 3.3 on solids, liquids, and gases. Our learning objective here is to represent the differences between solid, liquid, and gas phases using particulate level models. So most of the things I'm going to cover in this one are probably going to be pretty basic and familiar to you based off of, prior science classes and such, but I'd be remiss if I didn't cover them since they're technically part of the official AP curriculum. So, as you probably know, matter exists in three states: solid, liquid, and gas. And the main difference between them has to do with the variance in spacing and motion of the molecules or atoms. So, in a solid, we have pretty densely packed atoms or molecules that are not really moving around. They can vibrate as the temperature is increased, and eventually they can vibrate enough to start moving. But while they're still in the solid phase, all of the atoms or molecules are going to be sort of locked in place. So then the main difference between a solid and a liquid is in a liquid, it's still all of the same forces holding it together, whether that be Coulombic forces or intermolecular forces. Um, but in this case, for a liquid, things are slightly less densely packed just because things are moving around more. And also, none of the atoms are locked into a position. They can freely flow throughout the material, yet still not technically overcoming the forces holding it together, because that's what's happening in a gas phase. Once they get enough kinetic energy from heating, that they're able to overcome the forces holding it together, the atoms can kind of leave the whole of the substance and just kind of move around on their own. And in this phase, they will have as much space between them as they can possibly find. It kind of depends on the volume of the container of the gas. So if we're talking about solids, they can be crystalline. So that means they are highly ordered. They have a regular geometric arrangement, which I've covered already. Or they could be amorphous, which means they have no regular order. So not all solids are packed neatly and predictably. Some solids have a very random arrangement. A great example of this is silicon dioxide. Um, it's naturally occurring as quartz, which is a common rock that is found on the Earth. It's also what most of the sand is made out of. And then you have glass, which is the exact same exact same chemical formula of SiO2, but it's completely amorphous. And it's usually made from melting down cores. I think a lot of glass is made of sand, and they melt it down and then re-solidify it, and it takes this new structure that doesn't have as geometric and predictable of an arrangement. So quartz would be considered a crystal, whereas glass is considered to be amorphous. And in either cases, since they're solid, the individual particles' movement is limited. So like I said before, they can vibrate, but they're not going to move to different positions. And the fancy wording for this is undergoing overall translation. Translation is a word for relative movement that is used a lot in physics. So yeah, the atoms aren't really going to be moving around very much besides sort of vibrating in place depending on the temperature. And the structure of the solid is influenced by the interparticle interaction and the ability of the particles to pack together. So this has to do with the intermolecular forces or intramolecular forces, how strongly the atoms are bound to each other, how strongly the molecules are able to interact with each other, and the size of the molecules and the shapes of the molecules. Because if you have sort of an awkward molecule, it's not going to pack together as tightly as, say, like metal atoms that are all around the same size that can make a neat little pattern like this. The particles in a liquid, as I kind of covered before, are now moving freely, but still in close contact with each other. They are still more or less densely packed, except they are now able to translate relative to each other and move around in the substance. And yet again, this is influenced by the nature and strength of the forces between them. So how strong the inter or intramolecular forces are. The stronger those forces are, the more heat is going to have to provided to get enough kinetic energy for the particles to move around more freely. And that usually influences the melting point of the substance, and then therefore the boiling point of the substance when you're actually taking the particles in the liquid and taking them away from each other completely. And in the solid and liquid phases, I kind of already mentioned this, but they're both very densely packed. And since the liquids are able to move move relative to each other, yet are still bound to each other through those forces. And because of this, the molar volume, how much volume there is per mole of the substance, is usually really similar in solids and liquids. Some solids are more densely packed than their liquids. Some liquids are more densely packed than their solids. But overall, the molar volume is usually going to be more or less the same. Um, Also, and in both phases, the particles are in close contact at all times. Though both solids and liquids will have vapor pressures like we talked about last time, so some of these particles will have enough energy to leave, but overall these things are densely packed and held together by their strong forces. And then lastly, when you're in the gas phase, the particles are literally in constant motion. They've gained enough kinetic energy to overcome all of the forces within the macroscale material, and they're able to move around freely. But depending on the size of the volume or the volume of the container they're contained in, they're going to be colliding and crashing into each other and crashing into the walls of the container, which will influence the pressure of the gas. But when we're talking about gases, we usually consider there to be minimal effects or forces between the particles. An example I've always given of this is like if you're in a liquid, you're kind of like in a room of people and you can kind of hold each other's hands and then switch hands and still be kind of attached to each other. Whereas if you're gases, that'd be like two people on opposite sides of the rooms, like running at each other and trying to grab hands as they're running in opposite directions with a strong force is usually not going to have much of an interaction. Sometimes the adjacent particles might come in close vicinity with each other, and if there is a really strong intermolecular force, there will be a slight deflection or a slight interaction between those two particles, but it's not going to be a constant interaction, and usually won't really affect the pressure or the motion of the particles that much. So that is all for solids, liquids, and gases, and I'll see you in 3.4.